Okay, I think we're going to get started. Welcome everyone to the 4th edition of our Carbon Smackdown series. My name is Jeff Miller. I'm head of public affairs. Today we take on something we see and use every day and likely take for granted. So can anyone tell me what that is? Audience participation time. Windows. Thank you very much. So our speakers today are lab scientists Steve Selkowitz and Delia Milliron, who are in the forefront of developing energy-saving smart windows that will both cut down carbon emissions and make our work and living spaces more comfortable. Steve is from the Environmental Energies Technology Division. He will discuss why high-performance windows are critical to designing tomorrow's low-energy buildings. Delia is from the Materials Sciences Division and Facility Director of the Molecular Foundry's, I'm going to get this right, Inorganic Nanostructure Facility, correct? Okay, thank you. She will reveal ways in which scientists are developing new nanomaterials that could revolutionize the way windows work. So for those who haven't been here before, we will start with the speakers. Then we will follow that with a Q&A session, which will run right until 1 o'clock if we have enough questions. So first up is Steve. Please welcome.
Thank you. Pleasure to be here. It's always great to talk about windows in rooms without windows. Not always true. We have some presentation spaces in the lab that have windows. I got hired here about 30 plus years ago because there was an energy crisis. And the perception was that buildings were an important part of that crisis or part of the solution, and maybe we could do something about it. The doing something about it part was, well, sort of freeze in the dark or sweat in the heat. And we said, well, maybe we can do something from a science point of view. Maybe we can change the technology, improve the technology, make a difference. 30 years later, I guess you could argue I've been a failure because here we are talking about the need to do more of this. Actually, we've done quite a bit, and we'll talk a little bit about that. And the equally exciting part is there's a lot more to do in the future. I want to start, let's see if we get the technology to work here. First of all, by saying that the way you get things done, the way you change the world, both do good science and change the world, is by working with a lot of people and organizations. And I want to acknowledge that we've got a great team here. You're seeing me up here, but I represent 20 or 25 or 30 people on the efficiency side who've been working on this very hard for a number of years. We have our sponsors. Without sponsors that have stuck with us for a period of time, we wouldn't be where we are. And lots of partners in the private sector, because one of the things we're doing now is we're approaching the science from the point of view of how to get it out into the real world and have impact. And you don't do that by staying within the bounds of Lawrence Berkeley Lab. So let's jump into this. Windows of the future. And so this was the Windows of the future 25 years ago. It's still Windows of the future now. We still need windows. And you'll see in a slide in a minute that people say, well, we can save energy by not having them. That doesn't make any sense. We need to make them important parts of low energy buildings. This is a critical aspect of this. And you'll see a number of examples of what that means. And one of the conclusions we've come to in 30 years is that things need to change. The windows need to be adaptable over time and place and climate and use. And that's where the switchable smart window piece comes in, and we'll talk about that in more detail. And ultimately, they need to be affordable. We're not talking about neat gadgets that you make in the lab and you can make one of, and that's the end of it. We need to make stuff that's deployable at scale, and if it's deployable at scale, then it needs to be affordable. Now, I've been doing this for a while. You may not recognize me here. Actually, I've been doing Windows for a while. This was my junior high school science fair project. I'm pitching this as a low carbon. This was, if you can read it, an experimental boiling water reactor. I built a little model of it. I explained it. I'm not sure whether I won a prize or not. This was at a time when nuclear was the wave of the future. It was going to be too cheap to meter and all that good stuff. When I got to college and beyond, I changed gears a little bit, but you see, I've been in low carbon energy supply for a long time. So let me paint the context here, though, and the context is important. This is a view of energy use in the country, and buildings are the single largest end use, and they're the fastest growing end use. And you look at the numbers on the order of 40% of our energy, 40% of our carbon. The electricity, whoops, sorry, wrong button. Almost 3/4 of the electricity in the country. So you hear about smart grids and all that. 3/4 of all the stuff generated by all the power plants in the country ends up keeping the lights on, keeping it, building hot, warm or cold. So this is a huge issue. If you burrow down one level then and say, okay, where's the silver bullet? Can I do one thing in buildings that will save all that energy? The answer is no. And that's because look at homes, look at office buildings, and look at where the energy goes one level down in detail. And you find out there's lots of different end uses here, and you have to address all of them. Now, I've done a little calculation here. If say, what impact does windows have? Windows impact heating and cooling on homes. That's about 40%. And heating, cooling, and lighting in office buildings, that's almost 2/3. So they're a big factor. If I look at this slightly different way, windows are about 20% of all the heating and cooling use in the country, which is the single largest use, about 10% of all building energy use, and about 5% of the entire energy use in the country. That's a pretty big number. It turns out to be about $40 billion a year that leaks out the windows, something that we want to do something about. Now, what do we do about it? So this is actually a slide from a long time ago, sort of 1970s. The code guy said, well, windows leak lots of heat. Don't use them. I mean, this is what the slide was intended to say. If you sort of turn the clock ahead and look at what architects do, this is an all-glass building, happens to be one in Europe. And so here are the polar opposites. You know, either don't use them because they're lousy, or they're the way to save energy and the way to make buildings energy efficient. And as always, the truth lies somewhere between. And in fact, thinking more precisely about the role of windows, you sort of see here a conceptual diagram. You've got the outside world where the climate changes over enormous extremes, you know, freezing cold in the night in the winter and extraordinarily hot in the sun in the summer, and so on. And inside this building, inside this space, I want to keep this room between maybe, 68 and 72, and I don't want there to be water coming through, and I don't want the air to be rushing through. So the building envelope, as we call it, which is where the windows sit, is a modulator between the rapidly changing, dynamically changing outdoor world and the indoor world. And once again, it makes sense then that the technology that we want is going to have to be dynamic to adjust for that. Now, there's always a danger going into the lab, putting our science hats on and say, what are we going to do? And we're going to solve the engineering physics problem. But if we want deployment in the real world, we have to look at it more broadly than that. So this just reminds us that the solutions that we come up with that are designed to save energy need to do lots of other things. And in many cases, it's useful. Let's see, where's my favorite one? Acoustics. If you go from a single to a double glazed window, you reduce the noise transfer. So you can often market energy efficiency by coupling it to things that people know they like and pay for, whereas they don't always want to pay for the energy side. So let's look at scale here. As a researcher, what's the scale we can tackle things at? And the interesting thing about glass and windows is I've got a pretty wide range. At the level of the facade of the building, of the shape of the building, orientation, I'm working at meter scale. Windows are physically large objects. I can go down a couple orders of magnitude, just the thickness of glass, and a lot of what we've done for 20 or 30 years has dealt with glazing. But the exciting part, and this is where Delia and her colleagues come in, is looking in the coatings world, and I have it at the micron level here, but at the nano level also. So there's an awful lot of important things you can do, and this coatings activity has only really come into play in the last 20 or 30 years. If you looked at Windows solutions 40, 50 years ago, coatings weren't really available. So the whole new area here, and we're controlling a couple little bit of technical things around windows. The U value of a window is the heat loss and gain by temperature difference, and then much of what we'll talk about is the solar gain in daylight, the sun's energy that comes through. And there are a bunch of factors that we control here that deal with the intensity of the light, the spectral content, and so on, all of which can be manipulated by these parameters, but in particular by the coatings. And so if we think about this, a term called net zero buildings, our high-level goal is to get all buildings to the point where they don't use any net energy. That means you cut the losses way down first, and then you manage the remainder. Maybe you put PV on the roof, maybe there's some other option, and the small amount of energy that the building still needs is produced on site. That's the vision. In fact, that's the requirement in California by 2025, I believe, or 2020. All new homes are supposed to be net zero, and by 2030, all new office buildings. So there's a real challenge how to do that. Windows play a role. In a heating climate, you want to reduce the losses, but maybe let the sun in. In a cooling climate, you want to make sure that the sun is kept out, so you reduce the cooling loads. In all climates, you want to use daylight if you can. There's no point in having the lights on if the sunlight's coming through the window. And you might even turn the skin of the building into a platform for PV and generate power. Now, I mentioned before the issue of impact, and one of the things that the National Academy did about 10 years ago was they went back and looked at billions of dollars of DOE R&D investment and said, did this make a difference? And they came up with, in fact, a lot of the R&D didn't go anywhere. That makes some sense, I guess. But they looked at the energy efficiency area, and they identified 4 or 5, actually 5 or 6 areas, of which 4 of them were done at LBL, or we were involved in, one of which was advanced window coatings. And they concluded that for an R&D investment of about $10 million over a few years, the net impact on the country was $8 billion of savings. So, and this is all in a report heavily documented if you want to look into the details. So the answer here is that if you do good science and you understand where it fits into the economic side and the market impacts, you can in fact have an impact. And the people that are investing, the Congress and people are asking about, are we investing the right amount or too much in R&D? They want to see that impact. And Carbon 2.0 to some extent is about having measurable impact. So it's important to cite this. This is another interesting slide from the past here. You can't read the date, but this is 1988. I'm going to talk in a minute about coated windows, low-E coated windows, low-E glass coaters. And we showed that if you build a low-E coater and you look at all the glass that comes out of it and all the energy saved by that glass over the lifetime of the glass, it turns out to be about equal to the output of an offshore oil platform. Anyone heard about offshore oil platforms lately? This was 1988. There was some blowouts off Santa Barbara just before that. This is about a 10,000 barrel a day platform. The leak in the Gulf was bigger than that. But to first order, so the interesting comment is here is that we can save as much energy through efficiency as we produce with supply. And that concept still isn't well understood.
What was the numbers there? That was for all low-E glass in the country?
No, this is for, I could give you more details. This is to take one machine that produces so many millions of square feet per year. The machine has a lifetime. And then, so you produce, say, 10 years worth of coated glass, and then those windows have a lifetime in the field. So there's an accumulated thing there. And then here, we took the lifetime of the well, which we were told was 10 years. I can get you the detailed math. It's actually in the stuff you can't read here. But it's an interesting calculation. The main point, these are calculations that are good to factors of 2 or 3 or 5, but they're making a fundamental point about looking at efficiency as a resource. So let's talk about the opportunity here now. We want to do 2 things with windows, and I'm going to run through quickly some of what we've done on the insulation part, and then I'm going to introduce the dynamic control part, and Delia will talk more about the technologies there. Any one of these topics we could talk for hours, so I'm covering this quickly. We've got lots of stuff on our website, windows.lbl.gov. Email me, I'll send you papers, reports, documents. So let's talk about energy savings. And the first thing we discovered in the mid-70s was that one of the major losses of heat through glazing was long-wave infrared energy. So this is a spectrum, a radiation spectrum. Here's the solar world here, the solar spectrum and the visible part within it. And then here you have the long-wave radiation, which is the radiation emitted by room temperature bodies. And it turns out that a lot of energy lost through windows indirectly comes through this long-wave radiation. So if you could produce a coating, an long-wave IR reflective coating called a low emissivity or low-E coating, you could reduce the heat transfer in windows by about a third. So here's the schematic now. It's just a double glazed window, 2 sheets of glass. It's got this low-E coating on one surface. You can do some interesting things with the gas inside. The window looks identical to a normal window. You can't see because this coating is transparent and the visible, it looks clear, which is what it should. But it reduces heat loss by about a third. So we can go further with that. And those coatings now are in 60% of every window sold in the country. They didn't exist 30 years ago when we started. They're now a standard product. Everyone has them. You can go further with that, and here's where we go back into the research lab, going to triple and quadruple glazings. Whoops, sorry, wrong button. Triple and quadruple glazings with coatings and gas fills. We can evacuate the space between still the low-E coating. We can put a microporous material called aerogel in here. These are all ways of reducing the heat loss, and then we have to put it into a frame and a sash as well. Conceptually, what we're trying to do, notice the time scale here, is drop the energy loss of the window from single to double to low-E to more complex things down to the level now where we are, where the windows that we're producing, these triple windows with double low-E, are about as good as an insulating wall. They lose a little more heat at night in the winter, but they gain energy just because of the sunlight that shines through, even on a cloudy day. So we call them net energy gainers. So the window as a physical entity in the building is about balancing. Now, one of the problems with this stuff, I mentioned these coatings are often clear. You can't see them. How do you purchase a product or a capability that you can't see? And we end up with simulating and measuring them, ratings and labels. These are IR images. We run an IR infrared imaging laboratory here. And these are images of clear windows, double clear with an aluminum spacer and a lot of heat loss at the edge, double clear with a foam spacer, so we've now solved part of the edge problem. Putting low E in here, so the window gets warmer and warmer on the inside as you improve the conductivity. And now here we have what we call a super window, 4 lights, two or three layers of low E, krypton gas fill. So this is the ideal in terms of performance. So this gets us to how do you figure out, what combination of coatings, glass, gap size, gas fill, frame make up a window and provide performance. So one of the things we do for the industry is we've developed, again, over many years, a lot of hard work, a whole suite of tools that are used first by the manufacturers, and so they can more rapidly innovate and create new products, and now by architects and engineers and even homeowners. Some of this stuff is on the web. Last year, this is all available from our DOE-funded project. You can download them for free from the web. Last year, there were 90,000 copies of this software downloaded in the US. A few of them, I think, people found Windows and said, aha, I can get Microsoft Windows for free. But most of them, but I don't think that was too many. So anyway, so this has changed the nature of the industry and the use. And we also do things like we have tools on the web where you can, this is for a commercial building, an office building, you can log onto the website and put in an office module, an orientation, all the details, and press a button and get the energy use. So lots of outreach to help sort of get the information about how these things perform into the real world. Now those tools are backed up by measured data. Garbage in, garbage out, right? So we want to make sure, well, that's part of it too, but we want to make sure that the simulations are credible. So we have an array of test facilities, indoors, outdoors, that we've used as part of our program. So we have a fairly comprehensive, well-rounded program here. Recently, we received, with ARA funding, $16 million of new funding to build new testbed type facilities like this. This is 71T. It's up on the hill towards Building 90. A year and a half from now, you should see about 5 or 6 or 7 new things like this sprouting up in different places on the hill to test the emerging technologies here. So I want to conclude now with focusing on the solar gain and sunlight part of this whole equation. And just to show this enormous diversity of opportunities, of actually solutions out there. There's no sort of one way to do glass and do glazing. Now, there are lots of types of glass and types of coatings on glass. And the key issue, again, is keeping the sun out to keep the cooling loads down, but let the daylight in. You can easily put a reflective reflective coating on glass that keeps the sun out, but it doesn't let the daylight in. So we have this challenge here that's at the crux of the matter. So we're asked all the time by architects and engineers, okay, well, what should I do? What's the right coating? What's the right solution? And unfortunately, I mean, it's not just because we're scientists and want to do a little more work. Unfortunately, the answer is it depends on lots of things, and you can't give one simple answer. That's what makes this an intriguing, challenging problem. So we want Windows, out of this not very complicated thinking, in some sense, comes a conclusion. We want to be able to change the properties. It sounds simple, but if you asked this question 25 years ago, that's not the answer that you would have got. So as a conceptual framework, a lot of our work is focused on what we'll call a dynamic or smart building skin. So we've got the window, and it can change properties, either the glass or a shade. But behind the window is the whole infrastructure here. There are sensors, there are controls. I want to link it to the lighting. I want to link it to the heating and cooling. Even want to link it back to the power plant, because if energy is real expensive or hard to get mid-afternoon in the summer, maybe I'll control the window one way, and whereas if it's cheap or free or it's hydro or PV, maybe I can control it differently. So the whole issue of here, how do I manage this, becomes central to our research. So that's another important point of what we do. Aside from the materials work that Delia does and a lot of the related materials and engineering work that we do, we have people that work on control systems. Here we are, engineering control. So here's a control-centric view of the world. How do I adjust? So I want to control the windows and the lighting and the HVAC to drive building performance. But I want to do it based on all kinds of things, some of which I can control, some of which I can't. The task, the user preferences, what's going on inside, outside, and so on. So this becomes a challenging integration issue and a whole R&D area in and of itself, important to smart windows, but somewhat sensitive. Now, it turns out, as you might hope or expect, there's lots of interesting opportunities in the smart window world. We focused on the electrochromic ones, and Delia's going to get into this in a lot more detail. But again, we could spend a lot of time talking about the different options. Some are passively activated, so the temperature switches the window or sunlight switches your glasses, and then others are active. And we prefer the active ones because from the last 2 slides I showed you, we wouldn't be able to drive the solution. So just a few images in our test building. We've been testing these active coatings. We go from a test lab into some early demonstrations, doing some risky stuff here. These are the DOE headquarters buildings on the right here. And this is the office of the Assistant Secretary. So high-risk stuff here, right? You've got to get it right if you want to get more funding. Actually, it turned out to be hard to do this. And our program manager said, gee, I thought this was ready for prime time, and it kind of is, but it is hard. And my answer was, that's why we're still doing research on this. The coding wasn't the issue here. The controls integration was the issue. Notice that we're controlling different parts of the window differently. Now, because these electrochromic windows are not yet widely available on the market at low cost, and because we want to impact carbon rapidly, we've asked the question, can we control the gain in windows other ways besides coatings? The answer is yes. Blind, shade, shutters, lots of technology out there. And in Europe, these are European external shading systems. So this is that test facility you saw before, taking out the electrochromic coatings, now looking at shading. And looking inside, we're sort of trying to understand here how to control the solar gain, but let daylight in to keep the lights off, and just different views of how the shades. So these are motorized automated shades that can be dynamically controlled to adjust both the heat and the light. How do you scale this? So having done the work I just showed you for a while, we were approached by the owners of this. This is the New York Times building in New York City, 52-story, 1.6 million square foot building. And they came to us and said, can we do all that stuff you've done in your little test building at LBL? Can we do it in the real world? And we said, yes, but carefully. You don't scale from 100 square feet to 1.6 million square feet in one easy jump. We convinced them to build a 5,000 square foot mock-up in New York of a piece of the floor plate of their building. And for 2 years, we tested the technologies extensively, did a lot of R&D on not just the energy part, which is easy for us, but the human factors part. How do you block the light in a way that the people can see their computer screen? And I mean, these are news people still doing stuff visually. And all this instrumentation here, custom design, was designed to understand the glare issue and when to switch the shades. We're using shades here, not blinds. Why is that important? Because let's go back to the real world for a second, dollars and cents. So energy, as big as it is, $400 billion a year for the economy total in buildings, comes down on a per square foot of floor basis to about $3 per square foot per year. Collectively, a huge number on a building by building, floor by floor basis, not the huge driver. What's the driver? It's people. It's your salaries. So again, in your spare time, take your salary. I see some students here. Maybe you're volunteering or intern, but if you're paid professional here, take your overheaded salary, divide by the area of your office space, and you'll come up with a number like that, plus or minus a factor of 2. If your number's much higher, you're either overpaid or your office is too small, and likewise the other way. But so what we're pitching, and you'll see from Delia also, is that we're trying to manage the appearance of these coatings in a way where they are marketable because they deliver amenity and other value here as well. So final pitch here is focusing on the science part of this, both basic and applied. But we want real solutions in the real world, and in order to do that, we have to address process, people, policy, markets. Our division does that. We have policy analysts, we have economists, we have a really great team of people who are out there sort of helping the government write new codes and standards and understanding what the impact of those will be. And again, what makes the lab unique is the ability to do all these things together so that the technology that we develop in the lab actually has a pathway to the marketplace. And I think that's what we find exciting about the Carbon 2.0 initiative as well, which is to link the work we're doing in EETD with the science in the rest of the laboratory. And it's a win-win-win if we do it right. We'll solve this global carbon problem. We'll do it in a way that helps building owners and reduce costs, and we'll do it in a way that helps all of us do a better work at our job. So with that, I'm going to hand it over to Delia. And you're going to address them.
Okay, thanks, Steve. So I'm now, as promised, going to dive in a little deeper into one aspect of this smart windows problem and tell you how myself and some of the other scientists at the Molecular Foundry are looking for ways to leverage nanomaterials to further improve the carbon reduction capability of smart windows. So before I do that, I wanted to take a momentary step back and introduce you to the Molecular Foundry, which is our nanoscience research center here at Berkeley Lab. Within the Foundry, we're tackling the field of nanoscience from many directions. So for example, using advanced lithography techniques, we're making structures like this gold bow tie, which has a gap between the two parts of the bow tie of only a few nanometers, using these kinds of top-down methods, all the way to, on the other extreme, we're making structures like this peptoid helix, which mimics a natural protein and is assembled from the bottom up, from atoms and molecules, to create, in a particular sequence, this kind of structure. And we have scientists coming from different scientific disciplines, solid-state physicists in our theory division, chemists working in my group in the inorganic nanostructures facility, making inorganic nanostructures, and in the organic floor, making these polymeric nanostructures. So we're coming from all these different angles, and in many cases, we're looking for ways to leverage these new materials that are emerging towards carbon cycle 2.0 kind of challenges. So this is actually one example here from my colleague Brett Helms. This is a self-assembling polymer membrane designed for carbon capture. So that's one example, and of course, the windows that I'm going to talk about in a minute are another example. And as we think about these carbon problems and these energy problems, I see some common requirements that sort of frame the problem for us. One of them is, as Steve pointed out, these are extremely large-scale problems. Energy use in the world is amazing, and so when we think about windows and window coatings, we've got to be thinking about coating tens of square kilometers with these materials. So that sort of sets one parameter on what materials am I going to come up with for this kind of technology. And partly because of that scale, a second one is low cost. At least on a per unit basis, it has to be cheap to reach that kind of dimensions. And finally, because we're often converting between different forms of energy in any energy technology, we end up with complex functionality. So a material that has to do two things at the same time and do them really well. So this is for a solar cell. You need to handle light and you need to handle electricity at the same time very well. And you'll see that that's the case also for these electrochromic window coatings, which have been a focal point for us to get into this world. And so here again is the inside of the Windows testing lab that Steve mentioned with these electrochromic windows installed. You'll see them colored on the left here and clear on the right. And this is a zoom in to just that active layer that does the color switching, so you can start to see how this works. So you have one pane of the glass in your window is coated with a transparent conductor. So again, it's transparent, so you can see through it. Looks like a window. This is the active layer. This is where all the good stuff happens in this tungsten oxide layer. And what happens from this transparent conductor is we allow electrons to come into the tungsten oxide film. And at the same time, on the other side, there's an electrolyte that can provide lithium ions that intercalate or insert themselves into the tungsten oxide. So when this process happens by applying an electric potential, the tungsten oxide becomes this dark blue color. And of course, you can reverse the process and make it clear again. So how does this help us save energy? Well, in order to answer that question, we can go back to the solar spectrum that Steve mentioned. So I'm not showing the far infrared heat portion. I'm just showing the sunlight that's beaming down on us and beaming down, therefore, on our windows. And this is another view of it where, again, I'm emphasizing that this chunk in the green here is visible. That's the light that we use to see. That's the light that we can replace our electric lights with. But there's just about the same amount of energy in the near infrared as there is in the visible. And this is not contributing to us seeing. It's really just providing heat. And in some cases, that could be a good thing to heat our buildings when it's cold. And in some cases, we may not want it. So what today's electrochromic windows do is they allow us to vary the amount of this solar spectrum that's coming through our windows so that we have heat when we want it and we can have less heat when we don't. So basically, when it's clear, a lot of light is coming through in the visible and the near infrared, and when the tungsten oxide is colored, less of it's coming through. And it turns out if you look at the spectral composition of the light, today's electrochromics do a pretty decent job of modulating the visible light, slightly less good job in the near-infrared, but they modulate both of them more or less together. Unfortunately, when they're dark in this blue state, which is when we don't want that heat coming in, where does all that light go? It actually gets absorbed by the tungsten oxide. So it's a little bit like wearing black and going out on a sunny day. You're trying to prevent heating, but your window gets really hot. So they have a secondary heating problem where they need to find another way to reject that heat after the fact. And I won't go through the technical details of how that works, but that's a challenge for that technology. Another one is that, again, they don't do the best job of modulating the near-infrared light. So what can we do about that? How can we improve these technology challenges? So Tom Richardson, who's one of the lab scientists here working in the Windows group, came up with one new material solution to this problem, which was a different kind of switchable window, which instead of absorbing the light and getting hot, actually reflects the light. So here you're looking at a prototype window, which is reflective on the bottom. It's reflecting the object in the foreground here, and clear on the top. And the way this one works is the reflective film is a metal. It's based on magnesium. And that magnesium can react with dilute hydrogen gas and make magnesium hydride, which is clear on the top. So it's a totally new materials approach to solving this problem, which addresses some of the limitations of tungsten oxide. And so here it is in action. You see the setup with the flower on the other side. Right now, the window is in its reflective state, so it's reflecting the vase. And you're going to see, as the hydrogen gas comes in and reacts with this magnesium film, that in real time, it switches actually pretty quickly over just 20 seconds or so, and is now clear, and you can clearly see through to the other side of the flower. So this is an LBL technology that was licensed by this Bay Area smart windows company, Solidigm. You might have seen them in the news just last week because they're starting to build a pilot plant to manufacture not this technology yet, but their initial technology, which is based on tungsten oxide. So again, as Steve said, starting to get some real-world impact, doing the science and getting it out through these connections to companies. Okay, so how does this reflective coating help us, again, reduce carbon emissions? So this is going back to that tungsten oxide coating. Remember, it doesn't do such a great job modulating the near-infrared, and it also makes a lot of heat that you have to deal with, whereas this switchable reflective coating can have very large dynamic range. It can go down to the point where it's reflecting almost all of the light, rejecting, therefore, almost all of the heat. And it works equally well across the visible and the near-infrared. So that's great, but as Steve pointed out, in some cases, you want to keep some of that visible light so that you can use it to see by. So where I got interested in this field was based on this question. Can we make a coating that switches very selectively in the near-infrared? So we're going to vary the amount of heat coming through the window by a lot, but we're going to keep our beautiful view that we enjoy in many places up here at the hill, and we're going to keep the light so that we can turn off some of these electric lights and further save energy that way. So that's the question. Can we make a coating that does this? So if you like, this is our view at the foundry. Many of you have equally nice views from elsewhere on the hill. And it would look like this with my window in one state. And I'd flip the switch, and to my eyes, it would still look the same. Right? So again, an invisible technology. But if I look at it with an infrared camera, if I look at something near the window and I see how hot will that object get, if I look at it with these infrared cameras that we have here at the hill, I'll see that in one state, that object doesn't get very hot. It looks very cool. In another state, it might get quite warm. And so that's the idea, is let's vary the heat while keeping all the light to use for daylighting. So again, we started looking for a material solution to this problem. Is there a material that has properties that look like this? And it turns out there's a class of materials called transparent conducting oxides, TCOs, which have optical properties that look intriguing in this direction. So this is an example of some nanoparticles of a TCO material that we made here at the Molecular Foundry. And this is what their spectrum looks like. And again, I've highlighted the visible part and the near-infrared part of the spectrum. This is the absorbance, so you can see it's basically 0 across the whole visible spectrum. In other words, it's transparent. To your eyes, you can't see it. But in the near-infrared, there's quite a significant amount of absorption, so it's able to reject that light from coming through your window if you coated it on there. This isn't yet dynamic. This is just a static optical spectrum. So what we're doing now is working to integrate these kinds of TCO nanocrystals into a new kind of electrochromic device to try to achieve that functionality I talked about. And schematically, it looks like this. So it's not so different from the tungsten oxide case I showed earlier. We have our glass. We have our transparent conductor that's able to deliver electrons. But in this case, because we have a film of nanocrystals instead of a dense film of material, we actually don't need to intercalate lithium ions. It's enough for the lithium to just hang out near the surface and be polarized, basically compensating the charge of the electrons. It's close enough by because we have a nanostructured film. And for those of you who have thought about batteries versus supercapacitors, conventional tungsten oxide electrochromic is very analogous to a battery. This is much more analogous to a supercapacitor, and that comes with it some additional advantages in that we can do this process very quickly because we don't have to wait for the ions to come in and out, so our window will be able to switch quickly. And in addition, it should be very cyclable. It should hold up really well over the entire lifetime of the window. We can switch it back and forth as many times as we want because there's very little stress on the material in going through this kind of process as compared to the intercalation process. So that's the technology we're working on to try to achieve this sort of modulation of the thermal load while keeping our light. So then our 1-2 punch basically against carbon is let's reduce our lighting needs and let's modulate our thermal needs at the same time by building that into the technology. So then we have to think about the other side, not just the thermal side. How do we manage the lighting to try to get the most out of sunlight? And so I'm going to do a little bit of a thought experiment on how to use sunlight to reduce carbon emissions. So here I am, starting with 100 units, arbitrary units of sunlight, and I'm thinking about how can I use them to reduce my carbon emissions. One possibility, of course, is that I can put PV panels on my roof. I can turn that sunlight into electricity, and a PV panel today has about 16% efficiency. I can use that electricity for all sorts of things. I can then power my lights. Use an efficient light bulb, put it in a light fixture, put that light fixture in my room, and by the time that light arrives where I really need it to do my work or to go through my day, I find, looking at all these efficiencies, that from 100 units of sunlight energy, I have effectively about 2 units of useful light in the place where I want it in my room. Whereas, if instead of putting a PV panel on my roof, I punch a hole in the ceiling, in other words, I put a skylight in, about half of the sunlight couples in pretty well through that skylight. Some of it bounces around where I don't want it, but in the end, I have about 25 units of light where I really want them being effective for me to see by from the original 100 units of sunlight. So you can see that, heads up, it's a much better bet to use the sunlight directly for lighting than to go through a PV panel and a light fixture. And now I can save the electricity from this and use it to power all sorts of other things, like my laptop, for example. So it makes a lot of sense to use the daylight directly where you can. Unfortunately, most of our rooms, we can't put in skylights because most of the rooms in the world are not on the top floor, or it's otherwise not practical to put in skylights. So we're stuck with windows. And windows really only provide effective daylight right near the window. So we're stuck with this problem. How do we get the light further into the space where we can directly use it to offset our electric lighting? That's not a new question. People have been asking it for decades and have come up with some solutions. These are some window panes that are designed to do exactly that. They are structures manufactured on the millimeter to centimeter scale, getting back to this scale question Steve was talking about. And as you can see, they redirect incoming light. So the idea is in your room, you could put these in the upper part of your window where they're not going to disturb your view. And some of the light that would have only lit the space right next to the window bounces further into the room, and it can be used to light space further in. So you can turn off more of your electric lights. So this is the concept of light redirection or daylighting. OK, that's great. Unfortunately, these have some limitations. They're not cost effective as currently manufactured. And in addition, as the sun moves through the sky, as it does every day and with the seasons, the angle of this redirected light changes. And so it's really only very effective for part of the day or for part of the year and so on. So we don't really have optimal energy savings from this kind of technology yet. So it's a new challenge for us that we're starting to think about how we can use nanomaterials to provide a cost-effective coating that could address some of these limitations for the upper part of your window and really send the light further into the room. Okay, so when you put that all together, what you have is a concept of the ultimate dream window in my mind, which of course has to have a great view. But in addition, it should take advantage of all these things we've been discussing. It should have excellent insulation, as Steve highlighted, is the immediate way to save energy. We should be able to dynamically control the spectrum of light in the visible and the infrared. How much light do I have to see by, and how much heating am I getting? And we should redirect some of the light further into the room. And when you can do all of this in a window, you should, in any climate, at any time of year, really be able to turn a window from a liability in terms of carbon into an asset. And that's really the goal. So I'll stop there and just say thanks to all of our collaborators in the Windows group, the Molecular Foundry. These are some of the people working on the electrochromic technology I discussed and on some of the other ideas that I discussed. And our funding also has been ongoing through DOE primarily. So thank you.
Okay, we're going to begin our question and answer period now. So I will work this side of the room, and my colleague Ross will do the other. Do you have any questions over here? Okay, now you're right in between, so I'll have to pass this up.
The technique of applying any of those newer coatings?
Sure, I can. So the materials I'm specifically working on can be coated using a solution process. So it's very analogous to what's being done for some roll-to-roll coating of solar cells that are in pilot stage at this point, to magnetic tape coatings that have been made on large scale for decades, this kind of stuff. They're coated from solution. It's also interesting to consider nanostructured materials that could be coated using the same coating processes that are used in Windows today, which are things more like inline sputter deposition. So again, collaborating with Steve's group, we're looking at opportunities to nanostructure materials that way, which might be a faster path to connecting with the industry.
Another question up here? Hold on.
So on the,
Wait. Hold on.
I have two questions actually. So on the nanoparticle, you change the absorption or you change the reflectivity of the window?
So actually, we're not completely sure yet in the integrated device how it's going to work. What I showed is probably primarily absorption and a little bit of scattering, which can become reflectance. But in the integrated device, we're going to have to measure it and see which fraction is which.
So you may run into this overheating window.
Yes, exactly. And I didn't discuss the details, but obviously it is handled reasonably in the current window technology, and we would rely on some of the same tricks that they use to dissipate the far infrared heat back out of the window.
So the second question is not a scientific one. So we're trying to make the energy cheaper, safer, and more sustainable. You think we'll use less in the future, or we just make them we use more?
We should certainly use less. I mean, we can build houses today that use 10% of the energy that typical homes use, so they're 90% or so less. There are even some that have reached this net zero I talked about if you put the PV on the roof. Well, sure. So the question is how you define cheap. If you look at dollars and cents in first cost, most of the things we're talking about cost a bit more. But look at the 5-year, 10-year owning cost. You buy the house and then you pay, say, $1,000 a year for energy bills, or you buy a slightly more expensive house and pay $100 a year for energy bills. And so one of the things that I talked about policy before, there are people working on policies, innovative finance, low interest loans, for example, that allow you to make that investment. So the bottom line is each month you pay a mortgage and you pay an energy bill. Our goal is to make sure the combination of those two is lower from day one. And we've demonstrated that you can do that. You can save 50 to 75% of the energy in a home where from the start the combined energy bill and mortgage is lower, assuming you can do the financing and get all the little details worked out. It's not trivial, but is eminently possible.
Ross, there's
Is there a significant energy cost associated with maintaining a given reflectivity for the window or changing it? I mean,
So there's very little dissipation, basically. They're largely passive. So the electrochromics use energy primarily while they're switching, and even there, they're pretty low-power devices. And there's very little dissipation over hours, which is how long you'll probably want to leave it in the colored state.
There are a couple of devices like LCD devices that require power all the time, but again, generally speaking, the power they require is small compared to the energy that they're managing.
So I'm gonna ask a question now. Steve, so responsible consumers are looking at commercially available energy efficient windows. How should they choose? I mean, what variables should they be evaluating before they make the purchase?
So one of the things that's worked pretty well in the energy world at the consumer level is the Energy Star product line, if you will. So if you think about appliances and windows and many other things, they have ratings on them. And if it's an Energy Star rated window, that means it's better than average in the climate that you're in. So if you want to do no homework at all and do quick, simple, safe stuff, pick an Energy Star window product. But you can do much better than that by going online to look at some of our tools or websites or things like that, and you can customize the window. So for example, if you pick the Energy Star window, you've got a window that's average for all of California. But if I live in a house and it's facing west with a tree shading the window, the optimum choice for me might be different. And we have the tools that let you probe into that and figure out those effects. It takes a little more time and energy to do that, but you know, it's worth a lot over a long period of time.
And that web address again is?
If you start with windows.lbl.gov, but if you want the practical address to the tool directly, it's www.efficientwindows.org. That's a website we've done in collaboration with the Alliance to Save Energy and the University of Minnesota, and that lets you go to any one of 250 cities in the country and log in and find out how 30 or 40 different windows perform and how much you'll save and what the effect of trees are and all those subtleties. So, thanks for the advertisement.
Steve, you mentioned in your talk that the Smackdown is a global problem. And even now, China's producing 35% more carbon per year than we are. And it's growing. And some projections are it'll certainly be twice or 3 times ours, maybe even 10 times more in the next 30 years. So for a real Smackdown, we need to address China. Now, there are 2 issues here. One is I don't know how efficient their buildings are compared to ours. And I'd like to know if you have any insights on that. And the second is does China really need more simple things, like just having shutters up? Or is the smart window something that will actually have a role there, and how much does the price have to get down if that's the case?
Okay, so China and India, I agree completely. If we don't work with and help China and India solve carbon problems, then we're all toast. We'll all be knee deep in water, or toast or knee deep in water. You pick your thing here. Now the good news is we have a China group at the lab, china.lbl.gov. We have a team that's been working in this area for 20 years. We have transferred some of what we've learned in the US to China. We've even taken one of those tools, that window tool I showed you, and translated into Chinese. We're working with the Chinese on standards. So we're doing a lot that we can there. But your second point is certainly appropriate, that the average investment that they're going to make is going to be, all else being equal, going to be less than what we're doing here. And so the simpler solutions make sense. The beauty of this game and the challenge as well, and you know, I showed the blinds and the shades for a reason, because we have the same issues and options here. There's an array of solutions, and the trick and the challenge is to pick the most effective solution given your resources and constraints and given what's available. Some of those fancy blinds I showed you, those were imported from Europe. Even if you could afford them, you can't easily get them. So many choices, many options. Our role is to produce even more and to produce an array that spans, you know, cost and availability and all that as well.
A follow-up comment on that. Many people who come to my home, if they happen to be there in the afternoon, they're shocked when all of a sudden the shades start coming down. And they say, where do you get one of those? And I say, at the shade shop. So the information isn't getting out. The things that are available aren't even known by most people.
Yeah. So we struggle with that all the time, and we could spend, we've got money to do research and money to get the word out, and there's frankly always a challenge of, well, sometimes the sponsor will say, spend it this way, but we always try to do both, and you're exactly right that there's an awful lot of solutions out there now. I mean, as a general rule of thumb, we'd say that if we simply use the knowledge we have on the products we have effectively, you could reduce energy use by 20 to 50%. And what we really want to do aggressively for net zero future and saving carbon is to get from 50 to 80%. So that the 20 to 50% we can do if we pay attention to what we have today. The 50 to 80% needs to be enabled by the kind of research that we're talking about here. And again, there's a continuum between them, and the details obviously vary with the situation.
All right, first of all, thank you for all the hard work you do in this venture. I want to break it down more to the individual level, individual consumer, homeowner level, if you will, in the sense that, say somebody has a home 10, 15 years old, it's got, the dual pane windows and everything, but not in a mode to reconfigure the house or replace every window and invest in new technologies. Are any of these coatings going to be available to apply to existing windows? So the current homeowner with minimal investment can get immediate savings?
Sure. So for the traditional coatings and products, there are things like storm windows. You don't see a lot of that in the Berkeley climate, but in other parts of the world. And we're putting low-E coatings on storm windows. There are glue-on films that add some of the low-E effect. So once again, the challenge is to figure out, first figure out what's available, what's out there, and as we're saying here, not everyone knows. And then in this case, to figure out what do you put on when. As we're both talking here about the need to balance light and gain and so on, it's possible to put the wrong kind of coating or the wrong product in the wrong place. There's also another activity in our division called Home Energy Saver. And this is more broadly, I mean, the other thing, frankly, although I'm a kind of a Windows guy here, we're both Windows people for this presentation, we obviously do a lot more than that. Maybe if you've got $1,000 to invest, Windows aren't the first place to do it. So Home Energy Saver, I think it's hes.lbl.gov or Google it, gives you the whole array. You put in your zip code, here's what your house does overall, and lets you look at windows, heating, cooling, furnaces, appliances, and everything. So that's part of that optimization problem as well. That energy efficient Windows site I mentioned at the moment concentrates on Windows, but for exactly the reason you're talking about, because it can cost $5,000 to $10,000 to replace the windows in your home. So we're now working more aggressively on the retrofit market and lower cost options, and there are a lot of them out there today. And again, if you need some help locally, I don't want to get inundated, but send me an email and we'll point you in the right direction.
When I see these strategies to save energy, I also think about how much is the whole energy that is involved, not just in using the savings, but also the energy that's involved in producing this product, maintaining the product, and then disposing the product. Do you do also this type of research, for example, for this type of window?
Right. So life cycle analysis, LCA, is an increasingly important element. In general, again, sometimes generalizations are useful, sometimes they lead you down the wrong path. But in general, if you look at windows generally, the embodied energy, the life cycle energy of the window is the embodied energy is small compared to the operating energy. So from a life cycle perspective, you should pay more attention to the energies, the operations. Now, as you get to more and more efficient windows, and the energy use is now lower, now adding in much more glass and aluminum and coatings and so on could tip that balance. And the coatings we use today, the sputtered coatings, these are relatively energy intense in terms of some kilowatt hours per square foot here, although that's small in terms of life cycle. But Delia's world is looking at self-assembled coatings, maybe out of organic solutions. And those could be done possibly much more energy efficiently than the sputtered coatings. So lots of opportunity there as well. But that's not, I mean, for people, we sometimes hear, don't use efficient light bulbs because the cost of the light bulb is more than they save, or don't turn lights off because the inrush current exceeds the savings. That's bull. So pay attention to energy use, and again, there are websites and resources like ours to help if you need them.
Hi. Work on electrochromic coatings has been going on for a number of years now, and if they're in the marketplace, I don't know that I've seen them, but I guess my question is when do you see a significant penetration, and if and when that happens, might it happen perhaps first in vehicles rather than buildings?
We maybe both take a shot at that. So you're right, coatings have been around for a while. Really only commercially available in the last year or two in buildings is a company called Sage that makes a good product that's out there now. It's very expensive. It's in the range of $50 to $100 a square foot, which is beyond the price most people pay, but it's great for certain niche markets, and you can offset costs for cooling systems and shading and so on. The goal of the research, kind of innovative research we're talking about here, is to bring the cost down, by factors of 2, 3, 4, 5 to get the cost down to $5 or $10 a square foot, $20 a square foot, in which case it's much more cost effective. The company that was recently funded, the company Solidyne that we've licensed technology to and just announced last week they're opening a new plant in Mississippi, they're going to make this stuff at scale, and they have cost targets that are somewhat lower. So there's probably a half a dozen companies out there, all of whom are aggressively looking at the coatings, and all of them are trying to tackle the cost problem. Now, there are products in cars. Mirrors in cars have been on the market for years. The new Boeing 787 has electrochromic windows, I believe. The Airbus 380 has them. Sunroofs in cars have them. They're, in absolute total cost, are not too expensive. On a per square foot basis, they're still pretty expensive. So the buildings are a challenge. As Delia said, we have to get huge areas out at very low cost, whereas if you do a rear view mirror, it could be 25 or 50 bucks, doesn't seem like a lot, although on a per square foot basis, it's huge. And if you want to add anything to the cost issue.
I would only add on the cost question that if you look on a per square foot or per square meter basis, the numbers don't look so different right now for solar PV, which is something else I work on, and electrochromics, and actually the cost targets don't look so different in that, as Steve said, it's a factor of 5 or a factor of 10 cost reduction that people are looking for. In solar, the relevant number is dollars per watt, but it's also a factor of 5 everyone's trying to get to. Where it looks really good for Windows is that the scale of manufacturing right now for electrochromics is much, much smaller than PV. So the potential for sort of simple cost reduction that comes almost automatically as you scale up manufacturing, I think is quite significant. So I'm optimistic that as things go to greater scale, that some of that will be realized, even without changing things too dramatically about the technology and the way they're manufactured.
So we have one last question right here.
So I really liked your thought experiment, Delia, where you showed the efficiency of how much units you get there. And so while you mentioned that it's not so easy to put skylights everywhere, obviously, but is there any ideas of developing kind of fancy or intelligent light shafts? Because, I mean, that's a little bit provocative, but you guys have here mostly wood houses, so in a wood house to put in a shaft is not so difficult than if you have a big stone house in Germany. So is that an idea where you guys thinking of developing?
Yeah, and so for residential, there are quite a few pretty practical, pretty cost-effective options that bring light beyond the top floor already, just with good architecture, basically, I think. But for big buildings, for commercial applications and so forth, there are a number of more exotic technologies that have been constructed and actually do work for piping light into the building. And I had a slide on that, but I took it out to show you some of these things. Fresnel optics to couple into fibers and bounce light around, and it ends up in the basement. These things actually have been demonstrated. And again, it comes back to a question of cost effectiveness. If you're thinking about a system that tracks the sun for the most effective light coupling, it's similar to PV or concentrated PV, where the motorized system adds a lot of cost and so on. So that's why we're looking for things that can be done dynamically, but all in a coating in a localized way that doesn't require mechanization and these sorts of things.
So thank you, Delia and Steve. Thank you, everyone, for coming. Join us again next Monday, the 9th, the last in our Carbon Smackdown series. Thanks for coming.